I wanted to finish off the method of Frobenius with a couple of examples that show some special circumstances. So let's go ahead and start. Example 3. Y double prime plus 3 over x y prime minus 2y equals 0. Now here, let's go ahead and do our usual things. We'll set, and once again, look here, this is to the power of at most 1. Underneath the 2 is to the power of, well, 0, so it's less than or equal to 2. So we can go ahead and use the method. We're guaranteed at least one solution. So as usual, set y equal to k equals 0 to infinity, a sub k, x to the r plus k, and go ahead and throw it into the differential equation. So when we have y double prime plus 3 over x y prime plus 2y, that's equal to 0. Let's go ahead and throw our differential equation, or our Frobenius series, I suppose you'd call it. Not exactly a power series, but a Frobenius series. Let's go ahead and throw it in. So when we take the second derivative, we'll have, as usual, r plus k times r plus k minus 1, a sub k, x to the r plus k minus 2, plus 3 over x times the sum k equals 0 to infinity, r plus k, a sub k, x to the r plus k minus 1, and then finally plus 2 times the sum k equals 0 to infinity, a sub k, x to the r plus k. Oh, I better be careful. This problem is a minus. I need that there. And let's do our usual stuff to get the indicial equation. Here I'm going to, as usual, pull out x to the r. This is all equal to 0. And that will leave me with r plus k times r plus k minus 1, a sub k, x to the k minus 2. Now here, I'm going to pull the 3 over x inside. At the same time, I am, well, I guess I'm not. I think I'll do it right now. Here then we'll have a sub k. When I pull, this is like x to the negative 1 in. I'll get x to the k minus 2. And then the last one, I'll pull just the 2 in. I'll leave the minus there. Oops. And let's see where everything starts at. For this, starts at k to the negative 2. This, oh, actually should be k to the negative 2 as well. And this starts at k equals 0. Let me go ahead and release the first 2 terms from these first series to get the indicial equation. And so when I do that, for k equals 0, I'll get r times r minus 1 a sub 0. plus 3r a sub 0. All of that stuff is attached to a sub 0 x to the negative 2. And then next we're going to have the terms with k equals 1. So I'll get r plus 1. And then here when k is 1, those will cancel and I'll get times r. And then here I'll get 3 times r plus 1. A sub 1 x to the negative 1. And then I'm going to leave this series, well, I'll leave the rest of the series alone, but they'll all now start at the same place. So we'll get a k equals 2 to infinity, r plus k times r plus k minus 1, a sub k x to the k minus 2, plus, I got the sum, k equals 2 to infinity, 3 times r plus k, a sub k x to the k minus 2, and minus the sum, k equals 0 to infinity, a sub k x to the k. Of course, all that equals 0. And let's see what happens next. Let me go ahead and do some simplifying in here. Here, I notice I have, oh, I brought the a naught twice. I shouldn't have done that. Okay, so let me go ahead and pull an r out of here. When I take the r and factor it from here, I'll get an r times an r plus 2. And that's attached to a sub 0 x to the negative 2. Here, I'm going to factor an r plus 1 from both of these terms. So I'll get r plus 1 times r plus 3, a sub 1 x to the negative 1. Now, let me go ahead and re-index the last series. Meanwhile, I'm going to put these together here. And we'll go ahead and get everything set up. We have r plus k times r plus k minus 1. And then we have a plus 3 times r plus k. That's attached to a sub k x to the k minus 2. And then this series right here, I'll re-index it to start at 2. So minus the sum, k equals 2 to infinity, a sub k minus 2, x to the k minus 2. Now then, in the indicial equation, I have r times r plus 2 equals 0. So the stuff attached to a sub 0, r times r plus 2, so r equals 0 and r equals negative 2. There's our two solutions. So neither one of these make these 0, so that forces a1 to equal 0. So let me go ahead and set a1 equal to 0. And then we'll work on the series itself. I'll go ahead and pull this a sub k minus 2 in. We'll get the sum, k equals 2 to infinity. Here, I'm going to do similar to what I did up above. I'm going to factor out an r plus k from both pieces up here, and that will leave me with an r plus k minus 1, but then plus 3. So I'll have an r plus k times r plus k minus 1 plus 3. And that'll give me an r plus k plus 2. And then I will have attached to that a sub k. And then over here, I'm not exactly sure where that went. Let's go ahead and go back up here to see if I still had it. I'm not sure why I've forgotten that, but there it was. And all this, of course, is attached to x to the k minus 2. As usual, we're going to set this stuff equal to 0. So we're going to get a sub k, let me set this equal to 0, a sub k is going to equal 2 over r plus k times r plus k plus 2. What I'm going to try to do this time is streamline the process by doing my r equals 0 and r equals negative 2 at the same time. And so if I start with r equals 0, then I'll get a sub k will equal, when r is 0, I'll get k times k plus 2 a sub k minus 2. And then when r equals negative 2, I'll get a sub k will equal 2 over k minus 2 times k, a sub k minus 2. Alright, remember the k starts at 2, so when k equals 2 over here, I get a sub 2 equals 2 over 2 times 4 a sub 0, which is 1 over 4 a sub 0. On this side, I'll do k equals 2 as well. I get a sub 2 will equal 2 over 2 minus 2 times 2 a sub 0, and we see there's a problem right there. Having a 0 in the denominators makes this is not going to work. And I can see the problem up here. Let me grab this stuff right here and show you what the issue is. If we try to put in r equals negative 2, watch what happens. I get k minus 2 times r equals negative 2. We'll make the other part just k, like I said. A sub k minus 2, a sub k minus 2. Now when you try to plug in k equal 2, when k is equal to 2, this is the 2 minus 2 times 2, a sub 2 minus 2a sub 0. Remember, this is supposed to equal 0. And that, of course, zeroes out, and you're left with a sub 0 equals a 0. Well, with a sub 0 equals 0, and with a sub 1 equals 0, that means that I'm not able to get a second series from this method. I'll explain what the issue is in a minute. I can at least get one answer, and that's all that Frobenius' theorem ever promised, was that we would get at least one answer. So when k is equal to 4, or I'm sorry, do k equals 3 first. I get a sub 3 equals 2 over 3 times 5, a sub 1, and that, of course, is 0. K equals 4. So I don't need to do the odd ones, because when I get to a sub 5, it'll reference a sub 3. That'll be 0. I'm just going to have even ones then. A sub 4 will equal 2 over 4 times 6, a sub 2. Do a little canceling here. And that will be 1 over 4, so we have 1 over 2 times 4 times 6, a sub 0. K equals 6. I have a sub 6 equals 2 over 6 times 8, a sub 4. And we see what that one is. Let me do a little canceling first. So, I think, I don't, to be honest, let's just go ahead and do, I'm just going to multiply it out. I think instead of trying to find a pattern, this finding a pattern really hasn't done a lot for me anyways. So let me go ahead and put this back. I have 1 over 12 combined with the 1 over 4 gives me 1 over 48. And then here I have 1 over 24, 1 over 48. So that'll be 24 times 48. A sub 0. And that will be 144 times 2. Let's see, that's 288 times 4 would be 1,152 a sub 0. And that's plenty, I think. So this was all connected to r equals 0. So when our series, when we write these as y equals cy1 plus cy2, c2y2, y1 is equal to x to the 0 times 1 for the a sub 0, and then we have plus 1/4 x squared plus 1 over 48 x to the 4th plus 1 over 1152 x to the 6th, and this goes on forever. Now the question is, if we want a second one, how do we go about getting it? Well, believe it or not, the way you go and get the second, a way of getting the second answer is you can let y2 equal uy1. If you remember, this is reduction of order. And then, now you can do all bunch of stuff, but earlier, or look in your book or whatever, there's a formula that results from plugging in and doing all the differentiation and everything. And the y2 formula looks like this. You're going to have y1 times the integral of e to the negative, and in our case, 3 over x, which is the coefficient on y prime. And then you're going to have to divide by y1 squared. What that means, in order to get this, you're going to have to do y1 times the integral. Here, if you integrate this, this will be e to the negative 3 ln x, or it'll be x cubed, x to the negative 3, so we'll end up with x cubed in the denominator. y1 was 1 plus 1/4 x squared plus 1 over 48 x to the 4th plus 1 over 1152 x to the 6th, plus that goes on forever. You may wonder, how in the world do they plan on getting you to get this answer? That's even squared. So you have to use a squaring mechanism for this. And the indication from all books is that the only way you're really going to get to be able to do this is to invoke some sort of a computer algebra system. You do not want to try to do this by hand. Squaring it is a pain, then you've got to multiply everything by x cubed. Then, in order to do 1 over all that stuff, you have to do long division. And then after all of that's done, you still have to take that infinite series and multiply it by y1. This is all better done with a computer algebra system. So anyways, let me give you an idea of what you can do to do this on a computer algebra system. Here I have a Hewlett-Packard calculator here. I've been playing around with the series command. First, what I would do is start by squaring the polynomial. So we'll have 1 plus 1/4 times x squared. And you're going to have, you're not going to be able to put dots in this calculator. You're going to have to just settle for several places here. 1 divided by 48, and that's times x to the 4th. And then we have plus 1 divided by 1152, and that's x to the 6th. And I'll stop there. So you're going to have to definitely pick your accuracy if you're going to go this route. I should warn you, I am not going to ask you any problems that do this kind of stuff. Let's just go ahead and square this, and if you hit enter, it doesn't like what I did. The calculator here requires that I put multiplication symbols, so I missed that multiplication symbol there. So let me get it in and try it again. If I square it, you can see what you got to do now is hit some version of simplify, and it'll multiply it out. I know it's horrible, but then you can just kind of work your way here. Times, and then we're going to take x to the 3rd, and we'll enter that. So it's gone and taken all this stuff out here. So it's not the worst looking thing in the world. Now what I want to do is take 1 over all of this stuff. So there's a command that I was investigating inside of its catalog here called series. And I can take 1 divided by, and if I can take the answer to this and hit enter, and it does all that for me. And then there's another command that I can use called int, and I'll put my answer in here, enter. So you can see now this stuff here, if you're willing to live with x to the 6th accuracy, we're good. It just says this is order size. Anything greater than x to the 6th is just getting shoved back here. I'm sure that I have control over all that. Now, that's not it. I'm not done yet. Remember, I got to take all of this and multiply it by y1. And maybe if I luck out, I have y1 up here somewhere. Let's see if I can find it. Here, this is close enough. Let me copy that and take that 2 out of there. So, actually, I'll just change it to a 1. And I can take this and multiply it to the answer. Enter. And hit simplify. And you can see, here's my answer. If I click on here, I can even have it scroll there. I don't know if hitting simplify again will do anything more for me, but this will give you plenty of things. If I go and simplify again, I'm not really sure what it does for me. Let me go over here. Oh, here we are. So my first several terms are right here. And you can see you would have to do some more work to get all this, but it's sure a lot better than trying to do all this by hand. Long division of something like this means that you put whatever you get down here on the outside of a division bar, you put 1 on the inside, and then you're going to have a bunch of negative exponents for the x's. So this is one type of series that will cause you to have only one answer, and to get a second answer you have to do something like this. It's recommended that you use a CAS for a situation like this. I have another type that I wanted to throw up where a different situation happens. And let me go ahead and throw that in here. This will be my last example with these series. Both of these topics that I have on here today are not something I'm going to give you a test on, but they do complete all the situations regarding the Frobenius series. So here, this one is xy double prime plus 2y prime plus xy equals 0. We'll do the same stuff that we normally do. We're going to set y equal to, and if you do the little trick where you divide by x and you have 2 over x, that'll be to the 1 power. And over here, when you do x over x, it'll be to the 0 power. Frobenius's theorem guarantees at least one solution. So as normal, we'll do this, y equals k equals 0 to infinity, a sub k x to the r plus k, and we'll plug it into the series. So I'll get x times the sum k equals 0 to infinity, r plus k times r plus k minus 1, a sub k x to the k minus 2, plus 2 sum k equals 0 to infinity, r plus k a sub k x to the r plus k minus 1, and then plus x times the sum k equals 0 to infinity, a sub k x to the r plus k. All that's supposed to equal 0. Let me go ahead and pull in my stuff from outside. I will get the sum k equals 0 to infinity, r plus k times r plus k minus 1, a sub k x to the r plus k minus 1, plus I'll pull in the 2 there, 2 times r plus k, a sub k x to the r plus k minus 1, and I'll pull in the x on the last one. Of course, all that's equal to 0. Now, I'll go ahead and pull out my x to the r. And that will leave me, and at the same time here, since these are both going to be to the k minus 1, I'm going to go ahead and put those together. All right, and I'm going to do, I'm not going to spend as much time doing this. I'm going to kind of do a little fast. I just want to get to the meat and potatoes of this and explain what will happen when I get to the indicial equation and whatnot. As before, you'll probably notice that you can factor out an r plus k from these two pieces. And when I do that, I'll be left with r plus k minus 1 plus 2. So that will give me an r plus k plus 1. So we'll have r plus k times r plus k plus 1, a sub k x to the k minus 1. Of course, some reindexing and stuff's going to happen, and releasing of terms. Here, I notice that this starts at k to the negative 1, and this or not k to the negative, it starts at x to the negative 1, and this starts at x to the 1. So that's a difference of 2. Let me go ahead and release the first two terms from here. And so when k equals 0, I'm going to get r times r plus 1, a sub 0 x to the negative 1. And then for the k equals 1, I'll get r plus 1 times r plus 2, a sub 1 x to the 0. And then I'll have plus the sum k equals 2 to infinity, r plus k plus 1, a sub k, x to the k minus 1, plus, now what I'm going to do here is this starts at x to the 1, and this starts at x to the 1, so what I'll do is re-index this one, so I'll start it at 2. Of course, we'll get a sub k minus 2, x to the k minus 1. Of course, all that's equal to 0. Now let's take a look at our indicial equation here. We have r times r plus 1. We could set that equal to 0. And notice that you get r equals 0 and r equals negative 1. Now this is interesting here. Check this out. When r equals negative 1, it also zeroes out here. So in the case where r equals negative 1, you get both the 0, you get 0 times a sub 0, 0 times a sub 0 x to the negative 1, plus 0 times a sub 1 x to the 0. Well, what this doesn't necessarily force a sub 1 to be equal to 0 if this happens. Let's go ahead and let r equals negative 1 for a moment. Let me also combine these while I'm at it. So I'm going to put together k equals 2 to infinity. Let me go ahead and put my negative 1 in here. I'll have a k minus 1 times, it looks like I'll have times k, a sub k, plus a sub k minus 2, and all of that is attached to x to the k minus 1. Don't forget, our final answer, I'm just interested in this piece in here. I still have the x to the r out front that I'll put for my answer. And so let's go ahead and see what happens then. You'll set these equal to 0 as you normally do. But now let's see what happens here when we have, well, let me go ahead and solve for the a sub k. A sub k will equal negative 1 over k minus 1 times k, a sub k minus 2. So now k starts at 2, and so I have two free constants, a0 and a1, running around. And these jump by 2. So take a look at this. When we have k equals 2, I have a sub 2 equals negative 1 over 2 a sub 0. But then check this out. When k equals 3, I have negative 1 over 3 times 2 a sub 1. Now these two things are going to go ahead and generate two independent series where on the right I'll take care of the odds and on the left I'll take care of the evens, and these will all be attached to r to the negative 1. So we have k equals 4, a sub 4 equals negative 1 over 4 times 3 a sub 2, which equals 1 over, that's right, I forgot, I'm not going to actually do this anymore. It really doesn't do much for me. 4 times 3 times 2 is equal to 24, a sub 0. Then when I get over here to k equals 5, notice if I were to throw it into on this side over here, it would reference back to the a sub 1. So I get negative 1 over 5 times 4, a sub 3, which equals 1 over 5 times 4 times 3 times 2, which is 120 a sub 1. I'm seeing an interesting thing here, a series that I might recognize by the time I get done. K equals 6. We have a sub 6 equals negative 1 over 6 times 5, a sub 4, but that's equal then to 1 over 720, negative 1 over 720, a sub 0. And then over here, k equals 7. we have negative 1 over 7 times 6, a sub 5 equals negative 1 over, here 720 times 7 then is 5,040. Actually, you know what I'm missing? I probably should have mentioned here. When I do k equals 8, I've noticed then that what I'll get is a sub 8 will equal 1 over 8 factorial a sub 0. And then when k equals 9, I will get, well, I meant this was a sub 3, a sub 5, a sub 7, a sub 9. That will end up equaling 1 over 9 factorial a sub 1. So I probably should have been cognizant. Here's the one time when I decided not to do trying to figure out a pattern, and here a pattern actually emerges. So anyways, take a look at this. We can get a y1 and y2 right off the bat. Both of them are attached to x to the negative 1. So what's inside that's different? Here, we're going to have only even powers. So we're going to have 1 minus 1/2 x squared plus 1 over 4 factorial x to the 4th minus 1 over 6 factorial x to the 6th plus 1 over 8 factorial x to the 8th, and that will go on forever and ever and ever. And over here, what is this? This here looks like the series for cosine. And on this one, we're starting at A1 is in control of this. We're going to only get odds. We're going to have x minus x cubed over 3 factorial plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th plus 1 over 9 factorial x to the 9th, and that goes on forever and ever and ever. Well, this was a series that really was nice because y1 equals x to the negative 1 times cosine of x. And y2 is x to the negative 1 times sine of x. Well, this is really nice then. We have y, for our answer, y is c1y1 plus c2y2. I can simplify this a great deal just by putting out 1x to the negative 1, c1 cosine of x plus c2 sine of x. So that was really a nice final example to do in terms of this. I was not aware that it was going to turn out to be so nice before I started this problem, but there you go. So what is it that made these last examples different? What made them different was the indicial equations. Here, if you look at the r values, the two answers differ by an integer. And on the other one, where I only got one answer, before I was forced to maybe do all this horrible stuff to get a second answer, what happened with those two zeros for the indicial equation? Well, they too differed by an integer. What happens when you differ by an integer is when you start to work at the series. Remember, the series go through increments of whole numbers. So whatever you do at negative 2, if you start at a negative 2, if you take and change this to a negative 2 and you have k minus 2, well, when the series goes and 2 units later, you're going to go over the same coefficients that you had before. A lot of times, this weird stuff will not zero out, but what will happen is you'll get a repeat of the coefficients you got. The recommendation then is to always, if you're going to do a series, usually try to, I'm guessing, start with the one that has the higher R value, maybe the lower. It just depends on how it works out. Sometimes weird stuff like this will happen. So remember, Frobenius's theorem does not guarantee 2 solutions. It guarantees 1 solution. But as long as the answers, or the zeros for the indicial equation, do not differ by an integer, then you should be able to get 2 solutions. if they do differ by an integer, and that includes the situation where they are equal, you'll get one solution, but then you might have to do some work to get the second solution, or in this last example, you may luck out and get two solutions, but this was the first time when we actually made use of the A1, because the A1 was not forced to be 0. So I think I will end it there. I guess you can view this subject material as kind of optional. I doubt that I'm going to require anything, unless of course it shows up on a bonus problem somewhere, I suppose. But let's go ahead and end it there.